So there are a few common questions regarding the project. So the most common one is how to size the transistors. So if you look at the transistors here, it's 10 to 1. Right, it's 10 to 1 for these transistors, and you want to use the same ratio for C5. So for in C5, which is the one you have been using for the labs, we have, what's the minimum length? I think it's 2 lambda, right? (600 nanometers). So you want to use the length to be 600 nanometers, and then so the width will be 6 micron. Is that correct? Oh, it's 100 to 1, it's not 10 to 1. Is that 100 to 1? It is. You don't have to use 100 to 1. If you use 50 to 1, it's going to work as well. So the trade-off here is if you use wider, I mean, in the very beginning of the design, I think it's okay to use the wider transistors because you have a stronger driving capability from the circuit. So square law equation, which is used to calculate the current of the transistors is W over L, which is one of the factors in there. So you have wider transistors, you have more current going up and down, right? Being put up to VD or being put down to the ground. So whenever it's draining an inverter or draining any digital logic, it has more current to pull it up or pull it down. So it's just running the circuit more efficiently. You're going to have a higher speed of the circuit. So at the very beginning, if you use wider transistors, just verify the logic, make sure everything works. Then you can optimize the design to scale them down to save some space, and which is not really required for this project. You just need to make it work, no matter what's the size, right? We just need to get the first step functioning. So that's the first thing. Just look at the ratio here and try to use the same scale or same ratio from width to length for your C5. And another thing is this guy. So this is a little bit different compared to the other ones. So this is the PMOS, right? And because the source voltage here can go up to 2 VDD as a maximum. Remember when we are talking about the body effect, so substrate is a P-type semiconductor, but not really heavily doped compared to the P+. But it's still a P-type semiconductor, P-type silicon. And here's the N+, that's the NMOS, right? So we want to have a P+ here as a body contact, because as I mentioned in the test, there's no way to short the bottom of the silicon wafer to ground. There's no contact. That's not a way to do it. So how do you make the contact to the P sub? You have to dope a little P+. So these are both P materials, so they are shorted together, right? And then you can do whatever you want. Whenever you are doing anything, making any connections from this P+, you are connecting P sub to somewhere, right? And for the NMOS, we would like to connect the P substrate to the highest potential in the circuit. Or lowest? Which one? To avoid body effect. So what is body effect? So body effect is you didn't properly connect the body to the correct signal, which causes the changes in threshold voltage. So the reason is because it's a P and N, so it's forming a parasitic diode here. All right, it's a PN, right? It's a PN junction. So if you have the P potential at the P sub accidentally to be a little bit higher than N terminal, then it's going to draw current from P to N. So there will be a current flow getting into the channel. So current means it's getting positive charges into the channel. But for the NMOS, you have to apply a positive voltage to inverse the channel, right? So when you inverse the channel, it's actually attracting electrons in here. But the thing is, if you have a body effect, have a parasitic diode, it's injecting current into the channel, is actually neutralizing the electrons. So it's canceling the effort from the power supply, from the gate voltage, which is trying to turn it on. I mean, so it's going to increase the threshold voltage because it has to try even harder to inverse the channel. So that's called body effect. So the consequence is the threshold voltage, VTHN, increases because of the body effect. So to avoid body effect, you want to contact the P sub to where? You want to contact P sub, which is P plus, to where? To avoid body effect. That's the NMOS, right? So in your layout or schematic, where do you short the body of the NMOS? So you didn't do that, but in LT Spice, there's a body wire here. But in electrical VLSI, we connect the body wire. Since in electric, you are not seeing the force pin here because it's by default, it's already shorted to that place. And what is that place? Ground, right? If you ground it, so the P here becomes the lowest potential in the whole circuit. So there's no chance that the anode of the diode will be higher than the cathode. So there won't be any current flowing through it, right? So it's not causing the increase of the threshold voltage. So same thing for the PMOS. The PMOS is being built in the N well. And have to, if this is a source, right? Source, drain, gate. And so VSG, so it's going to be a voltage difference here, not this one. So where are we going to see a body effect? So PN, right? So there's the diode here. When there will be a body effect? So the potential here is higher than here. Then it's going to flow a current from P to N. So this voltage has worked super hard to attract holes. And now the holes, which are positive charges, are going to flow into the N well through the P plus. It's canceling the inverse channel. So it has to increase that voltage difference in order to turn it on. So also increasing the threshold voltage. So how to avoid that? The reason the current is flowing through the diode is because the P plus is higher, has a higher voltage compared to the N well. So what is the body for the PMOS? The body for the NMOS is the P sub, which is the silicon wafer substrate. Sub means substrate, right? So for the PMOS, so the P pluses are being fabricated in the N well. It's an N-type well. And also everything is still in the P sub, right? Because they are all built on one silicon wafer, which is a P substrate. So now the P sub has been grounded. But NMOS, if you have one single NMOS, the P sub is grounded, right? You cannot change it. You cannot change it in the PMOS because the PMOS is just it's just one device on the whole wafer. There are billions, millions of transistors, including NMOSes. And NMOSes have their P sub grounded. So these are grounded, right? You cannot change it. So now we're talking about, so what's the benefit to get the P sub grounded for the PMOS? See, the P sub is grounded. Is there a parasitic diode here as well? Yes. So if the P sub has the lowest potential, there won't be any current flow through it, which is fine. So it's not injecting charges into the well. So the pathway here is blocked. We are not talking about the p-n junction here, but there's another p-n junction over here. So we need a body contact for the PMOS as well. When you are laying out, remember, you're laying out an inverter, you have a top rail, you have a bottom rail. These are not just the metal wires, right? Yes, they are VDD and ground. But these are like has a green background, has a contact. So what are they? These are these things. The rails. If you just want to connect them to VDD, just use a wire. The metal 1, metal 2, metal 3, but they're not wires, remember? Okay, you have MOSFETs here, right? And you make the connection, that's the inverter. And connect the gates, that's the input and output, that's the inverter. Contacts here as well. Okay, so that's this thing, cross-sectional view. And so for there's an NMOS, which is this guy, and PMOS is this thing on the top, and the PMOS need a body contact. So the body of the PMOS is the N well contact, which is N plus. N well. I need an N plus here. Right, so the N plus is going to make a short circuit to the N well. So it's the body contact. You got that? Because N well is the body of the PMOS. The PMOS is being fabricated in the N well. So that's its body. And where do you want to short this pin to? Yeah, see? VDD. Why? Because VDD, if you short the N plus to VDD or the N well, which is the body of the PMOS to VDD, then the N well has the highest potential. So the cathode terminal of the diode has the highest potential. And it's not able to pass any current in that direction because it's what's that called? What kind of biased? Reverse biased. It's not forward biased. So the diode only conduct the current with forward biased, but reverse biased, no current. Some leakage, but not significant, right? So which can avoid current flow from the N well to the P plus, which is not desired, and to avoid body effect. However, for this circuit, for this PMOS is special. Why? So when you're looking at the schematic, always think about the layout, the physical layout, or the physical device in the cross-sectional view. So what's happening for the pi? If this is the pi, I cut it, look at the cross-sectional view of the pi, right? Right then you have nuts, whatever on the top. So for this PMOS, what's happening for this PMOS? You can see, look at the body. Here's the body, here's the N well contact. N well contact here. The source as a drain. I'm not connecting the body of the PMOS to VDD. Am I? No, it's connecting to the source. But for other PMOSes, let's find out another PMOS like this one. The body of the PMOS is connected to where? V high, right? So V high will be shorted to VDD or eventually. Is there another PMOS somewhere? There's another PMOS. It's also V high. So why is this PMOS? The bottom of the PMOS must be shorted to the source, but not the VDD, because it's the charge pump. Whenever you use a charge pump, the voltage here will be bumped to where? To VDD as a maximum. So what's happening for the cross-sectional view if you look at the device itself? So here's the PMOS. Here's the N-well. So the source can go up to 2 VDD. Yes, you can have another, there are many PMOSes, right? But you have to have a independent well for this PMOS, and you can control it in the layout. Actually, when you are doing the diffusion, you have to have an independent N-well for this guy, because all the other PMOSes, they are sharing the same N-well, and all the N-wells are being shorted together, and being shorted to where? VD. So imagine that if you short, here's a well contact, right? If you short this one to VDD, what's going to happen? As the other PMOSes, just do the same thing. You just connect all the N-wells together, right? Just share the same N-well. Cannot do that here. If you do that, then the voltage here will be VDD, and it's going to form a diode here, which is higher. This is higher. It's going to have a very strong body effect. So probably you won't be able to even to turn it on, because you can see the source voltage is 2 times compared to the cathode terminal of the diode. It's going to conducting a current in that way. So that's why in electrical VLSI it's different from LT Spice. You have all the devices have the 4 terminal, but in electrical VLSI you have to use a 4 terminal device, and you have to force the N-well to be connected to the source instead of, in electric VLSI you do not have the force pin. Remember, we just want to make it easier. But you have to find out the one has the force pin to be used as this one, because if you do not use that one, then it's gonna will be connected to the shared N-well or VDD by default. Okay, that's one thing you need to know. Okay, let's talk about the final exam. But before we do that, any other questions regarding the project? So you're expecting how many problems here? 6 problems on the final. It's so what's the time? I haven't checked the schedule yet. If they didn't change it, then it should be this time and the same location here. I'm going to double check the schedule again, since I put the time here at the very beginning of the semester. Hopefully they didn't change it. So it's December the 16th. Is that a Monday or Thursday? From 7:30 to 9:30. Oh, 2 hours. Okay. So it's 2 hours actually. Close book, close notes. And you can use a calculator. Can be a phone, I don't care. So what you need to study? AOI circuits, stick diagrams, and then convert everything into digital circuits after you know. Oh, they have to be in one line, one single line for PMOS and NMOS respectively. One line for PMOS and one line for NMOS. NMOS is C5 layers. So you want to take a look at. So the problem on the final exam can be a little bit more difficult compared to the homework assignment, but you do have a lot of examples to practice. Okay, so I'm going to just find out a snapshot from anywhere here. For example, I just provide you a picture here, and I'm going to draw a few lines here, 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 here to let you draw the cross-sectional view of the chip. Okay, definitely study it. If you do not prepare for that, you're going to fail that problem. Okay, very straightforward. Study it. And next one, the ring oscillator. And clock the circuit. And TPHL, TPLH, literally just as a problem here. This one, I think it's going to be, yeah, this one. Very similar to that one. I just studied this lecture, all right, and this problem. The operation of the SRAM. I know I didn't have a homework assignment for you guys, but I have a lecture recorded. You can watch it and understand the circuit. It's very simple circuit. Let me see if I have it here. SRAM. Did I record it? I didn't record it. then I have to take it out from the final. And the last one, BJT. So it's going to be number 10. We have 6 problems. number 10 is because we have all the numbers here. Right? So 10 will be BJTs. Okay. Since there are 2 weeks of lectures and notes, just look at that. Maybe only one homework assignment. That will be adequate. Just study that one. So it's very clear, all right? So there will be another problem. I'm going to replace the ASTRAM thing. Let me look at it, see whatever I want to put in there. Okay, I'm going to pick up one problem from any of the homework assignments. So to study the homework assignments, you should be fine. Okay. Okay, let's get a problem from the project. So just want to make sure you understand the project. So refer to the quiz we did for the project. Okay. Make life easier. So I'm going to just find out, maybe modify the problems or just use the same problem and just change the words from the most recent quiz. I think it's this one, quiz 6, right? Quiz 6, STARS ADC. Study that one. Any other questions? The project? Friday? Yeah, it's the end of Friday. Any before midnight? I don't really care. Yeah. So we want to post the report on the lab website. Yeah, I'm teaching microcontroller C351 and C433 in the spring. And in my mind, these are super important classes and very practical as well. So bad you're graduating. I mean, I really hope you can take it. So we students in the computer engineering program, they took circuit 1, they took circuit 2, they took analog, they took programming and C++. For the engineering student, they took robotics 1 and all the other courses. And eventually, I think in my mind, it's just preparing for these 2 courses. And whatever being used here, you can directly find it in the industry, especially for IPGAs. If a lot of companies are just directly using IPGAs to emulate their design, and that's it. And it's a very sweet tool to use because it's very repeatable. It's very tolerant to errors. Digital is just digital, just 1 and zeros. Doesn't like analog. Have to amplify. Have to look at the frequency. So the digital, you put efforts in there. You download it to IPGAs. It's going to work usually. Probably sometimes you have to debug it, but eventually you'll get it work. That's why people really love it. It's not requiring a lot of patience like what is required for doing analog design. And more importantly, it's being used for the companies to design digital chips, like whatever being used for your phone, your laptop. So I think these are critical techniques to learn, let you know. Okay. Anything else? No? Okay, so I still have office hours this week. So if you have any question, you can still ask me. You can visit even during the lecture time. Wednesday and Friday, we won't have any lectures. We won't meet. But I will be in my office, for you guys to come over and ask questions regarding projects, regarding finals, whatever. But it's better, if you can make appointment. So I will make sure I will be there. Okay. See you next week.